So yes, as you heard, my name is Julius Parulek, and I work in Equinor. And the team I am associated with is scientific computing team, or abbreviation SCOUT. And as Juraj said, so I'm quite happy to talk at this seminar. Because last time I talked on this seminar, I think it was like 5-6 years ago. So it's good to be back. Yeah, so I will start by, okay, so the talk is improving model, the title of the talk is improving model accuracy with history matching and visualization. So I will try to take you on a small introduction, like what history matching actually is, and how, in which way we are using visualization to reason about the data and the result of this process. I mean, the Equinor is a very broad company. Now it's basically labeled as energy company, but it's still the main sort of income or profit is basically obtained from oil and gas production. But slowly Equinor is moving to more renewables. So now spreading into wind farm industry, and so there is a lot of projects emerging in that area too. Equinor counts more than 21,000 employees, and they are spread in more than 30 countries. So it's a very large organization. The department building, which is the photo taken from, or it's basically Google Maps. That's the office in Bergen, which counts 3,000 employees, and also you can see where it's actually located. So it's close to the airport if you are wondering to go for a walk there. And so of course the office is closed now, only to some special exceptions. It has been closed for more than a year, so it's more like watching from outside. Yes, so but let me introduce the software kind of department that we have in Equinor. So the leader of the software department is Andrea Brambilla. So since October 2020, as this is also like very well-known name. Who was a PhD at VisGoup too, and he was basically a replacement for Jean-Paul Balabanian, who was also a PhD student in VisGoup. And so yeah, there are 45 currently employees in the software department, and 8 of them are purely from the visualization group. So Helvig is producing obviously a good, or Stefan, like good candidates. Besides, of course, like I would say the most of the employees we have actually are coming from the University of Bergen and also from NT and UNISAM, but the portfolio is very different. And also this is reflected what we actually do. So the biggest team, that's the scientific computing team, the SCOUT. It counts like 16 heads, and it's divided internally into 4 smaller teams. But besides, the portfolio includes development of like front-end applications, different web applications, analysis of data, for example, seismic data, that's a big thing, cloud computing, and different like web services that are associated with it. So, but in my talk, I will focus on the history matching. So, so what is the history matching? It's by a very simply put, it's a process where we build a set of numerical models, and in this case, when it's called a history matching, it's usually deals with reservoirs. In more general term, would be data assimilation, for example, like it's used in weather prediction. And we are not producing any arbitrary models, but models that should account for some measured data. So it means observations, in other words, that are produced by different sensors or different modalities, like, for example, acoustics, seismic. And the process, history matching, is quite complex. It actually is more like a workflow. So we are working with parameters from which we are building models. But these parameters are not well specified. So it means they're not well specified. They are specified, but usually as distributions. And this term distributions come from the fact that it includes a lot of uncertainty. And the workflow, when producing the simulating results of such models, it includes areas like geophysics, geomodeling, reservoir engineering. So it's quite complex, and such simulation takes usually like up to weeks. And those results are then matched again the observations or measurements, and then we are reason about the model. So we get like updated parameters, updated state of our model, and then the procedure starts again. So it's like iterative process. But let's go into more detail, like how this setup actually works. So imagine that this is our model. It's a let's say it's a reservoir. Why we can't really describe it, because for example, like Norway, reservoirs can be easily located several kilometers under the seabed, and they can be also pretty large. We are talking tens of kilometers in all directions. And so when talking, for example, about the shape, we are not really sure if this is the shape, or maybe it's a little bit bigger, or maybe it's a little bit wider. So it means this is basically the uncertainty. And we talk about all the different versions of this as realizations. So we have each parameter has its own realizations. In addition, we can have some internal properties of those models. For example, let's say that this yellow line represents like a water cut level, how we call it. Like you would like to know, like, for example, where the water ends, where the gas starts, where the oil starts. But again, we are not completely sure. So we can stick some kind of uncertainty band to it. So it can be lower, it can be higher, who knows. In addition, we have Equinor, of course, we're drilling wells, a lot of wells, and they have different sensors attached to actually the rigs. It can take samples from the reservoir, analyze the samples, and from there we have, for example, porosity, permeability. So it means how much it actually good for actually diffusion of water, and or even how much we are actually producing, like water and oil, for example, for a particular well. And the actual device that is measuring comes with its own uncertainty too. So therefore, there is again the band. As I said, we don't have a single well, but we have multiple wells. So the standard reservoir has like tens of wells. So it means that each well produces a set of measurements. So it's a lot of data we are working with. Again, we have more like external data, like measurement data too. For example, we have seismic data. So we have like some mines that are shooting down acoustics, and from there we have like a frequency response values, and from there we can either correct the models or build additional parameters that are included into the model. So when I summarize what we actually have, we have a model that is described by uncertainties, and this model is used for predicting new values. And these values, again, of course, come with uncertainties, because we have not a single realization, but a set of realizations, and thus those realizations actually produce another distribution. Then we have measurements or observations, which are again with giving uncertainty. And our goal in this process is to blend the prediction with the actual measurement. And we always start by some initial condition, initial state of parameters. So you can imagine this x0 being like a set of really initial parameters. So it's basically the ensemble. And firstly, we predict, then we update, and we reason about the data. One tool that is well handy for this kind of task is Kalman filter. Kalman filter was basically developed in order to exactly these tasks. So it means blending, if you have a model, for example, in this case, describing the motion of a train. So the train goes with a certain speed along the tracks, right? And we have different measurements of those trains. But our sensor, maybe the train is too fast, and we know that this sensor can be also faulty. So therefore, we have this uncertainty, like what was, for example, the position of the train over time. So how Kalman filter works? So we have the measurement initially, and we have our model. So our model predict that is corresponding to the measurement, and our model, the light blue square, predict a new position, for example, in a few seconds. But we have, of course, the new measurement there, and we use this measurement to correct the actual position of the train. So the red dot means like, okay, so this is pinpointing the exact spot of the train. So we took the measurement and the prediction and made a new state. The important ingredients in this process is something called state covariance metrics. So, as I said, we are not dealing with the concrete values of parameters, but with distributions. So therefore, this term emerges, so it's like state covariance metrics. And in this case, in a standard Kalman filter, this comes as a direct parameter, so it accepts metrics. Then we have observation covariance metrics that is actually accounting for the somehow noise in the measurements. And we have the process noise covariance metrics, which accounts how much we actually trust our models, because we cannot really say that the model we developed is so bulletproof. I mean, it can have its own basically problems. And to sort of deal with these covariance matrices, in 1994 was Geir Evensen, who actually proposed this Ensemble Kalman filter. And the major difference is that the system doesn't take as an input the covariance matrix, but instead it deals with Ensemble. So it means it uses Monte Carlo technique to actually sample the parameter space. So it means, as I said, the parameters comes as distributions, and this space is sampled in our realization. So it can have the number of ensemble members can vary. For example, for the reservoir modeling views, from hundreds to thousands of realizations. The more usually the better, but of course it's more costly and it takes more time. And basically, instead of sending directly these matrices, we are sending distributions, the ensemble members. Ensemble Kalman filter is also aimed at the larger systems. So it's the Kalman filter, as is described basically here, usually is meant for models that have linear behavior. So our model, for example, like computing the position of the train, that's very linear process. So it can be even basically represented as a linear transformation as a matrix. While Ensemble Kalman filter, here we are talking about processes which are highly nonlinear. And this is basically where this approach comes very handy. So working with directly different realizations. So again, so here we just to continue in this analogy with the train. So instead of having basically single prediction from the initial state, we take distribution of states, so where the train could actually be, and from each like the state we can predict new position, for example, over time. So I will now focus. I'm going to talk a little bit more about this Ensemble Kalman filter, just to have a kind of better idea how it works. Again, I have a very simple example of polynomial fitting. So imagine we have 5 observation points. These are represented as red dots, and our model is actually a polynomial function. Y equals ax squared bx plus c, right? And a, b, c are our model parameters. So we have 3 very nicely described parameters, and basically the prediction is y. So it means it gives us the function value at the particular x. So it's the domain. I just, for simplicity, I choose the domain to be from 0 to 9. The observations, so they are still represented as dots, but you will see in the next slide, actually, we have a value, then we have like the domain value, so it means 0, 2, 4, 6, 8, right? Then we have the fx, so the y value, and then we have the uncertainty. So the process actually starts with building the realizations. So we say, okay, so what is our initial condition, right? So we have initial condition for each of our 3 variables. So we have a normal distribution for point A, or for parameter A, B, and C, with its mean and variance. And based on these distributions, we are creating 100 realizations for simplicity. And so now I will talk a little bit like how we actually build the matrices. So this is the most mathematical stuff I will have in this presentation, but it's still very simple. So the equation itself is very simple. So the state covariance is just given by taking all the ensemble members, so all our parameters A, B, C, and creating matrix. Basically, we have 3 parameters, so the covariance matrix will be 3 times 3, and that's the state covariance matrix P. So that's how we do the covariance matrix. The other matrix is the observation matrix. So we have a bunch of observations, again with uncertainty, and from there we can create this kind of observation / measurement covariance. And in addition, we have the process noise covariance matrix. So it means how much, as I mentioned in the previous slide, like how much we actually trust our simulator, our simulations. So the lesser values in the covariance matrix, the more we trust actually. So it's like we are decreasing the uncertainty. But this is not always a good behavior. So let's say that after I apply this algorithm 2 times, so in while saying, okay, so this now I chose this process covariance to be rather big, so it's like 0.1. So we can see that even after the first iteration, so when I try to merge, to blend the prediction, the measurements. So these are the red kind of error bars, where the error bar means it's like what was the uncertainty, right? Then yeah, I mean, this is still the same. The scale just changed on the y-axis. But you can see that already all the realizations are getting closer to observations, and after the second iteration, the band is even smaller. So all the realizations of our model are really getting close to observations. If I am to decrease even more this kind of process covariance, so you see I'm very closely following the observations. Unfortunately, this is not the case in the reservoir modeling, because we never trust the simulation so much. Actually, they are very roughly describing the reservoir themselves. So I mean, this value is usually kept a little bit bigger. So let's get back to history matching. So that was just the illustration how the Ensemble Kalman filter works. In reality, we use a little bit more advanced algorithms. Like users can choose up to 4 different algorithms how to actually do this kind of blending of predictions and measurements. So again, we have our parameters and our observations in the beginning, and from those we create our first ensemble. So ensemble in our like history matching terminology means like the set of realizations with a set of responses. So what is a realization, like a single realization? Single realization is a sequence of different models and simulators that are using, for example, geomodeling to create a volumetric model of the reservoir, and then we use software for actually doing the simulations themselves. And then we have set of formal models and different tooling that are actually producing responses. Responses in this context are purely the function plots. So we have the curve that is saying like how particular attribute evolves in this particular model. Of course, and for actually this data, for example, it can be like how much actually water was extracted from this particular producer, or how much oil was produced. So this can be directly matched to what the models say. So therefore, for example, we have this red curve, which is actually the sensory data, like telling us like how far we are off. So what happens with this each realization, just to have a more clearer picture? So we are working with some kind of initial state of models, and each realization runs in parallel. So we have dedicated servers which are automatically instantiating a new copy of the realization. It downloads the model, then update the model with a new set of parameters, because we are drawing them from the distribution. Then we are simulating the model. After this is done, we are executing set of forward models. So it means it's a different tooling that is acting in a custom way on those results. Then we execute workflow jobs, which are basically binding all the realizations together, do some additional like results computations, and those results are then fetched and stored to some like global storage. So that's somehow in a nutshell, like how this works. I mean, this particular block, I mean, for each realization, it can take actually weeks to finish one ensemble. So therefore, the run needs to be really thought through, like if this is something we want. So therefore, we have a user in the loop who actually use visualization to reason like how actually parameters and responses correlate together. And then the user can decide, okay, am I to change, for example, the input parameters, the uncertainty of the observations, or can I just continue with the, for example, updating the ensemble 0 and producing a new ensemble, and then continue with another ensemble. So here we are talking basically a tree of possibilities. So user can take any ensemble and start basically simulating or producing new models from this particular ensemble. So again, here it's important to realize it's not a one concrete model, but it's always set of models. it counts from like from 100, 500, even thousands of models. Okay, so this is basically, so now I will talk a little bit about visualization, but just for illustration, so this is the data we are working with. So we have set of ensembles and the realizations, responses, parameters, observations. So this is the data space we are working with. So we were given the task to provide users to way to actually navigate in this space, and somehow also create dedicated views that anybody can access. So it means it sort of binds technologies. So we should develop software that is actually available for everybody. So it means it should be like web-based and stuff. So our goal is, as I said, is to create interactive visualization. So this project actually started just recently. It was in November 2020. And so the main currently data, I would say, models we are supposed to like create is for ensembles themselves. So they are simplistically represented as a graph-based kind of plots, where user can select a node of the graph and automatically such ensemble is selected. Then we have set of parameters, currently just selected from the list box. I mean, it counts really thousands of parameters. So we have some kind of regular expression queries that is helping to actually get down to the parameters, but it's obviously not enough. I will show you in future work. We have a lot of points in that aspect. And for the responses, we have the same. So we have just a very long list box of different responses. And again, user can select by writing regular expression, clicking, selecting multiples, and the like. By default, parameters are visualized as distributions. So it means we have one parameter drawn into a distribution. So it means it's a histogram. user can select multiple ensembles, and of course, all the parameters are then overlaid on top of each other. The same goes for responses. So we can have response from this particular ensemble, and of course, this response is present in all other ensembles. So I will just show you a brief demo, like how this actually works. I think I need to stop sharing because I need to share another screen. Yes, this one. Yes. So this is the current environment. So it's implemented in using D3 dash and Plotly. And in this example, we can see that we have 4 ensembles. So this was the initial state. And this is, for example, the last iteration of the ensemble run. So we have, and yeah, user can select it directly, or let's just select just the first ensemble by clicking on the response. So we get automatically as I said, all the responses are just function graphs. So we get automatically the function plot with all the values, where we can see the red error bars, which represent the observations with the uncertainty. So in this case, you can see that here we have 25 realizations, because I just created some dummy data. So also this model is just a virtual one. And for example, user can just append new views just by clicking, for example, on parameters. So this is, for example, parameter that is related to well OP1. Usually wells are named with this kind of OP prefix. While here, for example, this is a response like water oil production from well OP1. So we can directly see like this parameter might potentially be, might kind of drive this response in this kind of long simulation workflow. I mean, just by selecting multiple parameters, all is basically added up. So in these ways, user can easily compare so different plots. And now if I am to select, for example, another ensemble, so all views are automatically updated with this kind of new ensemble. So as you see, it's of course, like one can have different opinions, like whether this is the best way, but this is what users are sort of used to see. And so currently it's quite okay, appreciated. For example, here it's not so obvious that the responses, for example, in this 4th kind of ensemble run, should actually approximate the observations in a better way. So therefore, we have something called observation analyzer that is computing misfits. Misfits are somehow a statistical measure how far is the response away from the observation. For example, yeah, this one is very dense. Let's say that we take again this water oil production, which had 6 observations, and we see like this is actually level 0, so which means like, okay, so this is the observation and all the realizations. So here we can see all the 25 realizations in a box plot fashion. They are quite close to 0. So this is basically what we want in a way, but not so for the actually the prediction values, like for example in year 2015. So by selecting, for example, the later ensemble, so let's look at this set of models, and we can see, for example, like this ensemble is approximating the observation in a much better way. Then what is currently implemented is a simple correlation, or sorry, parallel coordinates, where user can just select parameters, show them as a parallel coordinates, and just seeing, like for example, parameters that are relating to wells, how they were actually changing between individual realizations. And again, by selecting another ensemble, we can already see both ensembles in one view. The most complex view, and I will just try to be very brief here, is the correlation analysis. So this is something that is quite new and is basically still work in progress, but it's this is something that really users want, and that's the goal of this view is to show like how a particular response correlates to a set of parameters. So basically, bigger values of response values mean bigger values of parameters, or other way around, then it's a correlation. For example, I can see that this parameter that relates to offset of well OP1 is highly correlated with this particular response. And I can, of course, select multiple responses, and then we have, therefore, there is this heat map of correlation. I mean, understanding this view takes a lot of effort, therefore I won't go into details. Just say that this is sort of the interaction that currently we are working on. So we're selecting responses, selecting parameters, always showing the scatter plot, like responses versus parameters, and again, which parameters are highly correlated and which are not correlated at all. Yes, so let me go back to the presentation. I hope that I will manage nicely. Just a second. Yes. I'm sorry, I restarted the presentation. Yes. So, I mean, this project is rather old, but the good news is that everything is public. So you can just go to this website, github.com equinor. This is the main workflow manager for entire system. But of course, the actual software includes tens of different libraries, packages which we are still developing, and many of them are also public. So many of the cases, example cases, you can run easily. We have a continuous integration development pipeline, because since we have quite a large number of users that are actively basically working on and using the software, so we needed to sort of do something about how we distribute the software. So we have actually daily releases called bleeding release, and it's very experimental. It contains always the recent changes in the main repository. Then we have monthly releases, which include like testing release, for which we have like 300 active internal users that are giving us feedback or requires new features. We have also like a subset of expert users. And every month we also do have like a stable release. So after the testing period is done, we are producing a new stable release. But of course, I mentioned, like, for example, some of the simulation runs over weeks. So therefore we are storing even the older stable releases. But but here we are really talking terabytes of data for this kind of deployments. The testing is very proper. So we have different property testing, integration testing, and unit testing. So it means every new feature we develop, it should be made in such a way, because we cannot really afford like losing, for example, running simulations that was running like 2 weeks and suddenly something will crash. And so that's sort of the reason why everything is so properly tested. Also, we have like a thorough code reviewing, and of course discussions with research experts and domain experts. The future work. So what actually regarding the visualization, this is currently really I would say actively pursued. So we had several rounds, like what is currently required, and as you can see, so we should, for example, do more selections on the realization side, so user can actually pinpoint particularization and show statistics only on those realizations. Implement link and brashing. This is very highly demanded feature, because since we are talking multiple views, so to have like a notion of selection and the corresponding visualization is necessary. Then we have requests for dedicated pods. So it means I haven't really mentioned like the terminology or prior or posterior parameters, but it's basically how the parameters change among ensembles. So dedicated plot just showing correlation of those parameters and different other correlation views. Not at the least, introduce clustering. This is especially since we are working on the domain of parameters which count hundreds of thousands of parameters, for example, like responses, because if we are talking volume, so each voxel, for example, produces a time curve. And so therefore, we can't really select like a single voxel, and instead like a cluster of voxels, for example, that are close to a particle.
Bavi telefon. Tamo je kod velikog telefona.
Was the question or?
I don't think so.
Okay. So a more general future work. So this project is currently the main Equinor project for the history matching, which is very important area, of course, for them. So therefore, it gets a lot of, I would say, attention and funding. So soon we will be actually opening more position. We want to actually create a new team because the entire project is slowly migrating to the cloud. So all the simulations and accompanying, I would say, all the realizations will be basically evaluated on a dedicated cluster nodes in Azure. And this, of course, reflects that we will need like a central storage and how to handle the data models. And so there is a lot of stuff including the last point, but it's, of course, there is more future work, is that we are having projects that are using the same system, for example, for optimizing wind farms, so positioning of turbines, orientation of blades. So this already looks very promising. And yeah, with that, I think I can conclude the presentation. So thank you for your attention.